Hello everyone, welcome back to this fifth video in a series supporting the self-study analysis assignment for the analysis of N of 1 trials. In the previous video we've sampled from the posterior. In this video we're gonna build a Bayesian model for continuous data, where in the previous videos we've been dealing with a binomial distribution where basically the outcome is a coin toss. We're gonna try and do this for continuous data where the outcome may be something like, well, magnesium concentration. So before diving into this, we're gonna talk a little bit about the normal distribution first. With this command I generate a random normal distribution with 1000 elements, a mean of 100 and a standard deviation of 10. Let me show you the histogram of this and also the density plot, which is sort of like the histogram, only smoothed. And here we can see that indeed the peak of this density plot is at 100, and about 95%, or actually 95% of the values would be between 80 and 120. So the normal distribution is parameterized by these two things: a mean, which is and the standard deviation. Now, from your high school math, you may remember that the mean is actually the sum of all the values of x in this case divided by all the observations of x. And in our code, this would be the sum of x, which is slightly over 10,000, and the length of x, which is 1,000. So if we have the division of both, we get 100 and a tiny bit and a fraction, so close to 100. Then the standard deviation takes a little bit more work to calculate, where the standard deviation takes a few steps. To get a standard deviation, basically what you do is we've calculated this mean, and from each element in x we subtract the mean and we square it. Then we take the average of this square difference, and we go back to the original scale by taking the square root, and lo and behold, we've got a standard deviation which is 9.7 here, so pretty close to the 10 that we inputted. Fortunately, R has some commands to do this for you, but this is just to show you that this is not black magic. These numbers are actually coming from somewhere, and it's pretty straightforward calculus. You just have to it's not even calculus, you just have to remember the rules. And if you don't want to remember the rules, R does it for you. So that's the normal distribution. Now we're going to load some actual data that's been observed by Howell and colleagues, and it's some data that contains the height of the Sun tribe, which is a tribe of hunter-gatherers in the Kalahari Desert region. And these people have been studied a lot because they are still on Earth one of the fewest remaining sort of original Homo sapiens, where there's a true hunter-gatherer culture. Not so much anymore, unfortunately, but still. So from this data frame we see that there's 500 and a bit people, and height has been collected, age has been collected, weight has been collected, and there's an indicator for whether someone was male or not. And from these people we're gonna select the adults. Now we want to create a model for the distribution of height among these people, and we can take from this distribution, we could say, okay, we know, for instance, the mean height for sort of the average Dutch person, which may be close to 178 centimeters, and we take some value for the standard deviation, where here the standard deviation is 20, which means that 95% of the values for height would be somewhere between 138 centimeters or 218 centimeters, which is wide, but you know, it's sort of the range that is possible. You would see very few adults with a height below this value of 138, or very few people who are above 2.20 meters really. And we can actually plot this prior for height and it would look something like this. So there's next to no observations between 100 and next to no observations between 250. So it's sort of, realistic. For the standard deviation, we can take a uniform distribution, which is basically saying each value between 0 and 50 for the standard deviation is equally likely. Based on this model, we can already make a prediction of what the data would look like. So say we've got, let me adjust this. So we've got this model, and we can take a sample from this distribution, where we take a normal distribution, 10,000 samples. For the average height, we take a uniform distribution, 10,000 samples for the standard deviation of the height, and we can combine these. So the mean we can take from our samples, we can take the standard deviation from the samples that we've generated, and we can get actually the prior height distribution based off of our priors and plot this. So based on these priors with the possible ranges for standard deviation and the possible ranges that we've inputted for the height, we generate this as a posterior, and this is without actually having looked at the data. So we see that if we combine these two priors, the prior for mean height and for the standard deviation, that adding the standard deviation prior expands our range a little bit. So now we can have values which are slightly above 0 up until 3 meters. Not completely realistic, but the most likely values are still centered around this 178. Now, we will combine these priors, which are sort of realistic, with the data. And we will do this using the quadratic approximation. A quadratic approximation is a slightly different way of testing possible values than the grid approximation that we used before. I won't bore you with the details, but in principle, it's the same thing. So here we have our model with the list function that we've seen in the second video, and here we have the model for height, which is saying height is a normally distributed variable with some value mu for mean and sigma for the standard deviation. The mu we assume to have a normal distribution with its mean we assume beforehand to be 178 centimeters and a standard deviation of 20, and the sigma we assume to have a uniform distribution, which means that each value is equally likely between 0 and 50. We add in the data and we run the model. Then we can summarize this, what we got out of the model, and if we add the data for the sound people, we see that the actual posterior mean is 138 centimeters and the standard deviation is 27.5 centimeters. Like we did before, we can plot the posterior height and make a density plot out of this. And this is what the distribution of height, of the mean height in the sand people would look like. So it's very close to 138, and actually we see that most values are, or the estimated mean is somewhere between this 134 and 142. This is the maximum a posteriori estimate, and we can also have the confidence intervals, or the highest probability density interval, and that is in this gray shaded area. So this is basically how you run a Bayesian model for a continuous outcome. Now obviously we've put the men and women and combined them here in this group, assuming that the men and women would have a similar mean height. Sorry. This may not be the case. To handle these different values for sex or possibly different treatments, once we start dealing with the magnesium data, we need to handle categorical variables and put these into the model as well to estimate different means for height for men and women, which we'll be doing in the next video. So thanks for your attention and see you next time.